A very pleasant good morning to each and everyone here. This is MD.SAMI, Assistant Professor, Department of ECE, working at Swarnabharati Institute of Science and Technology, Khammam. So today I am going to demonstrate on sky wave propagation. The contents which I am going to deal here are: what is sky wave propagation? How is it related to ionospheric layers? And how is it associated with the terms called virtual height, critical frequency, critical angle, maximum usable frequency, and OWF? Here OWF stands for optimum working frequency, skip distance, fading, and diversity. Before starting what is sky wave propagation, let me say what is ground wave propagation and what are its disadvantages and why we are going for sky wave propagation. So as the name suggests, ground wave propagation is also known as surface wave propagation because the electromagnetic waves will glide along the surface of Earth. And it is practically important at frequencies ranging up to 2 MHz. This is one of its limitations, which is mentioned as a first point here. Ground wave propagation exists for frequencies up to 2 MHz only. And the most important thing is, for ground wave propagation to exist, both transmitting and receiving antennas should be very large. They have to be vertically polarized and very close to Earth's surface. And this is the foremost condition for ground wave propagation to exist. And ground wave gets attenuated. What is the reason for its attenuation is due to surface irregularities. Here surface irregularity means Earth is not flat in nature, it is curved. There may be rivers, there may be mountains, there may be buildings, there may be trees, due to which the ground wave is going to attenuate. Last but not the least, attenuation increases with increase in frequency. Now these are the disadvantages of ground wave propagation. Now let us know what is sky wave propagation. Sky wave propagation is also known as ionospheric wave propagation. Why we are going to call it so? It is also known as ionospheric wave propagation because the EM waves will reach the atmospheric layer called ionosphere and then it will return back to Earth. I repeat, the waves will move from Earth to atmospheric layer called ionosphere and then they get back to Earth, and that getting back to Earth is called as refraction. Let me tell the difference between reflection and refraction. If the wave is incident at particular media, if it gets in the backward direction as compared to angle of incidence, then it is called as reflection. If the wave is incident and it bends and goes somewhere else, then that is called as refraction. I repeat, here the mechanism involved is refraction. Now see the definition here. The propagation of radio waves reflected or refracted back towards Earth from the ionosphere. And it is not limited by the curvature of Earth. Now you see the diagram here. Now this part, this indicates Earth and the upper layer indicates ionosphere. Now if the ray or wave is transmitted only once, if it is incident only once and reflected only once, then it is called as single hop. I repeat, if the wave is incident once and reflected or refracted once, then it is called as single hop. If the wave is incident once and it is getting multiple reflections, then it is called as multi-hop. I repeat, if the wave is incident once and gets a single reflection or refraction, that is called a single hop. And if it gets reflected multiple times, then it is called as multi-hop. Now there are different names for sky waves. These are also known as skip waves, ionospheric waves, or hop waves. Sky wave propagation can include multiple hops between the Earth and the ionosphere. This point I have already mentioned. What is a single hop and what is a multi-hop? If the ray is incident only once and get refracted or reflected by only one time, then it is called as a single hop. If the ray is incident only once and gets multiple reflections or refractions, then it is called as multiple hop. Now, the frequency range at which sky waves can operate is ranging from 2 MHz to 30 MHz. I repeat, frequency range of sky waves is from 2 MHz to 30 MHz, whereas for ground waves it is up to 2 MHz only. Now, the diagram shows single hops and multiple hops here. Now, this ionosphere is a region which is around 50 kilometers to 400 kilometers above the surface of Earth. In our school days, in geography, we learned that there are 3 layers of atmosphere such as troposphere, stratosphere, ionosphere. No, we are only dealing with ionosphere here. The layer which is about around 20 kilometers above the Earth's surface is called as troposphere. Around 40 to 50 kilometers above the Earth's surface is known as stratosphere. And the region which is above 50 kilometers, above the Earth's surface is known as ionosphere. And this ionospheric region is ionized by solar radiation. Solar radiation means the radiation which is produced due to solar activity. Now let us know what is meant by ionization here. Ionization is a process in which a molecule acquires a negative or positive charge by gaining or losing electrons to form ions. Now this is pretty clear, and this ionization takes place because of UV rays, alpha rays, gamma rays, beta rays, which are radiated from due to solar activity. Now, refractive index of ionosphere. Now, what is refractive index and why we are comparing the ionosphere, the waves propagating in ionosphere with the refractive index? Now, generally, we have different media such as free space media, conducting media, dielectric media. If a wave wants to propagate from transmitting antenna to receiving antenna via free space, it will travel at a speed of 3 into 10 power 8 meters per second, which is also equal to velocity of light. Here, the wave properties are compared with light, and light is determined by a term called refractive index. Now, this is also related to bending mechanism of ionosphere. As I already said that the sky waves get refracted from a layer called ionosphere and then get back to Earth. You can see it from the figure here. A ray is incident and then it is bent and it got back to Earth again. That figure represents regarding refraction. So from Snell's law, we have n is equal to sin theta I by sin theta r, where n is refractive index. Theta I is angle of incidence and theta r is angle of refraction. This refractive index has no units, which is given by n is equal to square root of epsilon r. Here epsilon r is a dielectric constant which doesn't have any unit, and it is again given as root of 1 minus 81 n by f square. Here n stands for electron density and f is frequency in hertz. Now there are different ionospheric layers such as D layer, E layer, ES layer. Here ES layer stands for sporadic E layer, F1 layer, F2 layer, and these can be shown in figure. Now take a look at this figure. Actually this is structure of atmosphere. This is the structure of atmosphere. Can you see the curved earth at the bottom? Above it there is a layer called troposphere. Above the tropospheric layer there is one more layer which is represented in the dotted form as stratosphere. The region between troposphere and stratosphere is called as tropopause. And upon that you can see D layer, E layer, F1 layer, F2 layer and outer atmospheric region. Starting from D layer to outer atmospheric region, all these layers, I repeat, starting from D layer to F2 layer, all these layers are called as ionospheric layers. Now you can also see troposphere is around 10 to 20 kilometers above the Earth's surface. Tropopause is around 20 to 90 kilometers and so on. Okay. Now this figure shows the virtual heights of all the layers, which we are going to discuss in the next slides. Now let us discuss about each and every layer of ionosphere in brief. Now this part is very important. I already mentioned the layers of ionosphere are D layer, E layer, ES layer, F1 layer and F2 layer. So let us have a look on each and every layer here. And this part is very important as far as your examination point of view is concerned. Now let us start with D layer, which is the first layer of ionosphere. Its average height is 70 kilometer, which means this layer is present above Earth's surface, and it is above the Earth's surface of around 70 kilometers. I repeat, the height of this layer is 70 kilometer above the Earth's surface. Now the thickness of that layer is around 10 kilometer. I once again repeat, the average height of this layer is 70 kilometers and the average thickness of this layer is 10 kilometer. The most important point of this is this layer exists during daytime only. I repeat, this layer exists during daytime only, and this is not useful for HF communication. Here HF stands for high frequency. As it is only present during daytime, it's not useful for HF communication, which indirectly means it is useful for very low frequency and low frequency waves. The most important point here is it reflects some very low frequency as well as low frequency waves. The electron density in D layer is given as n is equal to 400 electrons per cc. Here cc stands for cubic centimeter. I repeat, electron density of D layer is 400 electrons per cc. Fc it is critical frequency. Critical frequency of D layer is 180 kHz, and make a note that whether it may be refractive index or critical frequency, it doesn't stay same for each and every layer. Critical frequency also varies from layer to layer, as well as refractive index also varies from layer to layer. I repeat, critical frequency of D layer is 180 kHz, and radio waves does not bend here. That means there is no refraction taking place in this layer. Last but not the least, the virtual height of this layer is around 60 kilometers to 80 kilometers. Next, let us see the characteristics of E layer. The average height of E layer above the Earth's surface is around 100 kilometers. The thickness of this layer is 25 kilometers. And this layer also exists during daytime. And it reflects some HF waves. In previous case, it reflects only VLF and LF waves. But here in this case, it reflects HF waves. Its electron density is N is equal to 5 into 10 power 5 electrons per cc, whereas in the previous case it was around 400 electrons per cc for D layer, whereas for E layer it is 5 into 10 power 5 electrons per cc. Critical frequency in this case is around 4 MHz. In the previous case it was 180 kHz for D layer, and for E layer it is 4 MHz. Its virtual height is 110 kilometer. I repeat, its virtual height is around 110 kilometers. The maximum single hop distance covered by E layer is 2350 kilometers. I repeat, the maximum single hop distance covered by E layer, covered by a sky wave in E layer, is around 2350 kilometers. Now let us see the characteristics of sporadic E layer. Now the most important point here is this layer exists during both day as well as night. It is a very thin layer. Its height is normally 90 to 130 kilometers above the Earth's surface. Its electron density is very high, and it's difficult to know where and when it will occur and how long it will persist. Now there is a difficulty here. We cannot predict that when this layer will occur, and it's also difficult to predict, if at all if it occurs, how long it is going to stay there, how long it is going to persist there. Next, coming back to characteristics of F1 layer. The average height of this layer is 180 km above the Earth's surface. The thickness of this layer is around 20 kilometers. It combines with F2 layer at night, which indirectly means F1 layer will be present at night, as well as F2 layer will also be present at night. Now the critical frequency of this layer is 5 MHz. The virtual height of this layer is 180 km, and the maximum single hop distance covered by a sky wave in F1 layer is around 3000 kilometers. In this, some high frequency waves will get reflected from F1 layer. Some of the waves are also absorbed by the transmission media here. Now let us see the characteristics of F2 layer. The height of this layer is around 325 kilometers in daytime. The thickness is around 200 kilometers. But during night it falls to a height of 300 kilometers. In the previous case, we learned that it reflects HF waves, but it offers better HF reflection in this layer. The electron density is around 8 into 10 power 11 electrons per meter cube. Now there are two critical frequencies here, during daytime and during nighttime. During daytime the critical frequency is around 8 megahertz, and during nighttime the critical frequency is around 6 megahertz, and the virtual height of this layer is around 300 kilometers, and the maximum single hop distance covered by a sky wave in F2 layer is around 4000 kilometers. Now here we have seen some terms: critical frequency, virtual height. Okay, let us know what all these terms stand for and what is their importance in skywave. Now if you can see the figure here, the dotted line in the form of triangle upward from the curvature of Earth, that length is called as virtual height. From the surface of Earth, upon that you can see one more layer which is curved in nature below the triangle. Till there the region is called actual height. It's better understood here in this diagram. Now see here, first I will define what is actual height, and then I will say what is the virtual height. Now you see, something is written as ionized layer in between actual height as well as your virtual height. Something dash, some darkened line here. That is nothing but an ionospheric layer. See, at the bottom you can see ground surface. Here the ground is treated as flat surface. Now I am defining actual height. It is defined as a height above the surface of Earth. I repeat, actual height. It is the height above the surface of Earth at which a sky wave will return back to Earth after reaching the ionospheric layer. I repeat. Now